shifting using coherent detection. We know that the frequency shifting, that is for frequency shifting we are using two symbols, that is symbol 1 and symbol 0. For symbol 1 it is on one frequency and symbol 0 is on another frequency. Consider here in the binary PSK the symbols 1 and 0 are distinguished from each other by transmitting one of the two sinusoidal waveforms that differ in the frequency by a fixed amount. The symbol S1 is the symbol S1 symbol 1 S1 of t is equals to square root of 2 EB by TB cos 2 pi F1 of t. Therefore the bit duration, that is t, is calculated by duration of 0 to TB, and for symbol 0 we are written as a S2 of t is equals to square root of 2 EB by TB cos 2 pi F2 of t. So here also t varies between 0 to TB only. This can be written in general as, that is Si of t is equal to square root of 2 EB by TB cos 2 pi. Here F1 F2 generally represented as a Fi I of t, where t varies between 0 to TB only, and elsewhere the value will be 0, where the I and the values, that is I is equals to 1 comma 2, and here EB can be called as a transmitted energy signal per bit, and the transmitted frequency is said to be, that is Fi is equals to Nc plus 1 by TB for some integer value, that is Nc, and I is equals to 1 2. The orthonormal basis function is given by phi I of t is equals to square root of 2 by TB cos 2 pi Fi of t, where t also varies between 0 to TB only. Here the orthonormal I, where here the I represents, that is I as having the values of 1 comma 2, and j, here the coefficient Sij can be called as a, where I is equals to 1 comma 2 and j is equals to 1 comma 2. The coefficient of Sij is given by the Sij is equals to integral varies between 0 to TB, that is 1 bit duration, Si of t into, here I is there, no? So first Si of t plus for j we are written as a phi of j comma t, phi of j of t into dt, where Sij is equals to integral varies between 0 to TB. This Si of t can be written as square root of 2 EB by cos 2 pi Fi of t into square root of, that is phi j of t can be written as 2 into TB by cos 2 pi Fj of t into dt. So carrying out the integration, the Sij simplifies into, here Sij is equals to square root of EB, where I is equals to j, and when I is not equal to j, then the value will be 0 only. And consider the signal space diagram. Here we know that the two message points, that is S1 and S2, are coefficients are S11 and S12 are computed. Here S11 is given by the 0 to TB Si of t into phi 1 of t, here 1, that is orthonormal into dt. If we simplify this equation, we will get a square root of EB only, and when Si comma Si2 is equals to integral varies from 0 to TB S1 of t into phi 2 of t is equals to 0, because when I and j is not equal, then the value will be 0. If it is equal, then the value will be square root of EB. Like that, here the vectors vectors S1 is equals to square root of EB by 0. So for the next value, that is S21 is equals to integral of 0 to TB S2 of the 2 is there, so S2 of t into phi 1 of t into dt is equals to 0. So S22 is equals to integral of 0 to TB S2 of t into phi 2 of t into dt, where the S2 is written by the, this is square root of EB. So S2 of t is equal to 0 to EB. This is a signal space diagram is given by that this axis is a phi 1 of t and this is phi 2 of t. Here this is a decision boundary. Here there is a two message points, that is S1 S1 and S2 1. This is the message point M1 and this is the message point M2. This is an S2 and this is an S1. We know that the S1 is having the value of square root of EB by 0. EB comma 0. So square root of EB comma 0. And next here the second value, that is S2, is given by the 0 square root of EB. So 0 comma square root of EB. From here to this point we can call it as in 0 to 0 only. And this S1 is having lies in the region between this is the decision boundary up to decision boundary. This is the region we can call it as an S1 region, and from decision boundary here to here, that is 1 2 3 4 quarters. In the 4 quarters, first and the third, 1 2 3 4. So here the first and the third half, first half, third half and the fourth region we can call it as a message region 1 here. And here for the message 2, we'll get here the second quadrant here, first quadrant half, second quadrant and third quadrant half. That is you can call it it's in the region Z2. So this angle is called as, that is the decision boundary, and where the orthonormal is coincides, that angle we can call it as in pi by 4 here. And next is the BPSK.